Picture a neural network that has already memorized its entire training set. It scores nearly perfectly on every example it has seen. But hand it a new example from the same task, and it performs no better than random guessing. You might assume the model has failed and move on. But if you keep training, something remarkable happens. After a long, quiet plateau, the model suddenly begins answering unseen examples correctly. That delayed leap is the puzzle at the heart of this paper. The authors call this phenomenon grokking. It is a dramatic temporal gap between memorization and generalization. The model fits training data fast, then appears stuck, and only much later discovers the underlying rule that lets it generalize. Our goal is to understand when and why this transition happens, what controls its timing, and what it tells us about how neural networks actually learn. We will walk through the experimental setup that makes this phenomenon visible, inspect the key training curves, explore how data fraction and regularization reshape the timeline, and then confront the limits of what these experiments can and cannot explain. By the end, you should have a concrete mental model for why training accuracy alone is a dangerously incomplete signal. To see grokking clearly, we need a setting where memorization and generalization are easy to separate. That requires a very specific kind of dataset. The authors build their experiments on binary operation tables from finite groups. Each example looks like a math equation: A, operation, B equals C. But the tokens carry no built-in arithmetic meaning. The model sees them as arbitrary symbols. Think of it as filling in a multiplication table where you have hidden some of the cells. During training, the model sees a fraction of the table. At test time, it must predict the missing cells. If it has only memorized the visible entries, it fails on the hidden ones. If it has actually learned the rule, like modular addition or division, it succeeds. This design strips away the noise of natural data. There are no semantic hints in token identity, no language priors, no texture cues. Any success on unseen entries must come from discovering structure in how the symbols relate to each other. It is a perfect microscope for studying learning dynamics. The model is a small decoder-only transformer with roughly 2 layers, a hidden width of about 128, 4 attention heads, and around 400,000 non-embedding parameters. It is trained with Atom W and warm-up, and crucially, the training budgets are very long, up to about 1 million updates. That patience is what allows late behavioral changes to surface. One implementation detail matters. The loss is computed only on the answer token. The model reads tokens for the operation symbol, B, and equals, but only the prediction of C is supervised. This keeps the task focused on function learning rather than language modeling of the prompt prefix. So we have a deliberately simple world. Symbolic equations, partial table training, a model powerful enough to memorize quickly, and enough training time to reveal whatever comes after memorization. Now let us look at the training curve that made this paper famous. On modular division, with roughly half the table used for training, the model reaches near-perfect training accuracy very early, within about 1,000 optimization steps. But validation accuracy stays near chance for a long time afterward. Then comes the delayed jump. After an extended plateau that can last hundreds of thousands of steps, validation accuracy climbs sharply toward near-perfect performance. In their highlighted run, this happens only after roughly 1 million updates. The critical observation is not a mild late improvement. It is a dramatic temporal separation between 2 milestones, when the model memorizes and when it truly generalizes. The loss curves add an important nuance. Validation loss can actually rise first, as the model overfits harder, and then descend again later as generalization emerges. This echoes a second descent pattern, but the accuracy behavior is the clearest anchor. Generalization quality changes long after training fit is already saturated. A useful mental model is to think of 2 phases of internal representation. In the first phase, the network finds a shortcut, essentially a lookup table that stores the training pairs it has seen. In the second phase, continued optimization, especially under the right inductive pressure, gradually reorganizes the parameters toward a simpler, more compressible rule that extends to unseen pairs. The authors report this behavior most clearly near the smallest data fractions that still lead to generalization within the compute budget. With larger data fractions, training and validation curves tend to track each other more closely, so the dramatic delayed transition becomes less visible, even though learning is still happening underneath. Memorization happens fast. Generalization can arrive much later, and the delay itself is a measurable, reproducible phenomenon, not a fluke of a single run. With that dynamic in hand, the natural next question is, what controls the length of that delay? One of the paper's strongest results is a compute-for-data trade-off. Across tasks that eventually generalize, shrinking the training fraction does not necessarily reduce final validation accuracy, but it can dramatically increase the optimization time needed to get there. In their S5 permutation group experiments, near the critical regime around a quarter to a third of the table, dropping the training fraction by just about 1 percentage point can increase the time to generalization by roughly 40 to 50%. That sensitivity is striking. It means small dataset choices have outsized effects on when the model transitions from memorizer to rule learner. Notice the asymmetry. As training data shrinks, the time to fit training labels can stay roughly constant or even get slightly faster. But the time to reach strong validation can explode. Training speed and true rule learning are decoupled signals, and this data fraction sweep makes that decoupling quantitatively precise. They sweep many different operations: modular addition, subtraction, division, and permutation group products. An interesting pattern emerges. Symmetric operations, those where operation B equals B operation A, often generalize with less data than closely related asymmetric ones. The architecture apparently finds it easier to learn functions with certain invariances. A particularly elegant test strengthens that point. When symbols are abstract, addition in one modular representation and multiplication in another can be algebraically identical up to renaming. The authors verify that data efficiency curves for such isomorphic operations align almost exactly. This confirms that the model is responding to the mathematical structure, not surface features of the encoding. They also test a mixed operation that switches behavior based on whether one input is odd or even. Generalization still appears. This is significant because the target is no longer a single clean group law. The model can learn piecewise algorithmic structure as long as the overall pattern is still compressible. But not every task groks within the compute budget. A harder polynomial-like operation fails to generalize even with high training fractions and long training runs. This is an important boundary. Delayed generalization is not guaranteed. Some solutions remain pure memorization even with substantial optimization time. Data fraction controls when generalization emerges. Nearby tasks can differ sharply in difficulty, and the trade-off between data and compute is steep near the critical regime. Beyond data fraction, the next lever is how we optimize. Which training choices push the model from memorization toward rule learning? The authors run an ablation suite comparing weight decay, dropout, Gaussian noise injection, learning rate, and full batch versus mini-batch training. This gives a direct view of which pressures improve data efficiency within the same model family. Weight decay stands out as the single most effective intervention. In their plots, it often cuts the required data fraction by more than half relative to baselines without it. Generalization can still happen without weight decay, but the regime becomes narrower and far less reliable. They also compare decaying weights toward zero versus toward the random initialization. Both help, but decay toward zero tends to work better. This suggests that the benefit is not simply staying close to the starting point, but actively compressing the representation toward lower norm solutions that encode the rule more efficiently. Optimization noise helps too. Minibatch stochasticity and explicit Gaussian perturbations can both improve outcomes, consistent with the idea that noisy training guides parameters toward flatter, more generalizable basins. Learning rate sits in a sensitive band. Too low and the model never reaches the rule. Too high and training destabilizes. A subtle point is that full batch or low noise settings can still generalize when the training fraction is large enough. Randomness is not a magic switch. These factors shift how easily optimization finds a compressible rule before the compute budget runs out. They are catalysts, not requirements. Representation visualizations reinforce that real structure is being learned. For modular arithmetic, output embeddings arrange in circular or cylindrical patterns that mirror the underlying cyclic group. For S5 permutation operations, cluster structure emerges that aligns with known group-theoretic relationships. The model is not merely memorizing pair-by-pair answers. It has built internal geometry that reflects the mathematical rule. Regularization and noise do not just shift accuracy by a small margin. They can determine whether the model ever reaches a rule-like solution within feasible compute. Before drawing conclusions, we should be honest about what these experiments can and cannot settle. The authors probe robustness by injecting mislabeled outliers into the training data. Small amounts of corruption have limited effect on eventual generalization, but larger amounts noticeably degrade data efficiency and shrink the regime where grokking occurs. This outlier experiment clarifies something important about capacity. The network still achieves perfect training accuracy even with corrupted labels, so inability to memorize is never the bottleneck. The real question is whether optimization also discovers a simple rule alongside the memorized exceptions, or gets permanently stuck in a brittle lookup strategy. A preliminary flatness check offers another clue. On one S5 objective, sharper loss minima show a strong negative correlation with validation performance, around -0.8. That is consistent with the hypothesis that grokking corresponds to finding flatter regions of the loss landscape. But this is a single task with a single metric, so it remains suggestive rather than conclusive. The authors explicitly distinguish grokking from the familiar double descent narrative. In double descent, model performance dips then recovers as model size grows. Here, the dramatic shift appears over optimization time, not model scale, and accuracy often changes monotonically after the initial memorization phase. The timing pattern is related, but not identical. The most important caveat: every experiment uses synthetic symbolic datasets with compact vocabularies and controlled noise. This gives extraordinary resolution on training dynamics, but it means transfer to natural language or vision benchmarks requires care and dedicated empirical work. A fair reading is that this paper provides a microscope for studying learning dynamics, not a full map of deep learning behavior in the wild. The findings are strong on phenomenon mapping, moderate on causal explanation, and intentionally scoped to tractable algorithmic worlds. Let us close by distilling this into a mental model you can carry forward. Here is the core takeaway. Training accuracy tells you when a model can store answers. It does not tell you when the model has discovered the governing algorithm. In this regime, those are two different milestones separated by potentially vast amounts of compute. Keeping those milestones conceptually separate prevents a whole class of premature conclusions during model evaluation. For practitioners, the implication is patience combined with diagnostics. If validation is flat but training is perfect, you may be witnessing a delayed transition rather than a dead end. Monitoring both curves on a shared log-scale timeline is the single most valuable habit this paper motivates. For researchers, these algorithmic datasets offer a compact laboratory where optimization dynamics, implicit bias, and generalization can all be studied together. Data fraction, regularization strength, and noise each act as independent knobs on the delay between memorization and rule learning, giving fine-grained experimental control that is rare in natural data. The open frontier is mechanistic. We can see that grokking happens, we can measure what accelerates or delays it, and we can observe the geometric structure that emerges in learned representations. What we still lack is a precise causal account of the internal transition. How exactly does a network reorganize from a lookup table to a compressible rule? That question connects grokking to the broader agenda of mechanistic interpretability. So grokking is not magic. It is a delayed reorganization that becomes visible in controlled algorithmic settings, where we can watch memorization happen, wait patiently, and then sometimes see genuine rule learning emerge on the other side. The lesson is simple but powerful. Do not confuse